Welcome to AP Calculus Lesson 2.4a. Thank you again to Mark Sparks for providing the curriculum that we're working through today. In this lesson, we're going to be connecting the function and the derivative of polynomial and trigonometric functions. And we're going to look at this both graphically and analytically. For a large part, this is review and extension of what we studied in 2.2, where we found as we went through a chart that where our derivative equaled 0, we found our function had a horizontal tangent line. And where it had a horizontal tangent line, we also had the possibility of a relative maximum or minimum. And in fact, if it's a polynomial, then the 0 will in fact give us either a maximum or a minimum for polynomial functions. So it's important here that this should become automatic. If the derivative is 0, where my derivative is 0, I have a horizontal tangent line, I have a max or a min. Where my derivative is positive, I'm saying my slope is positive. When my slope is positive, that means I'm increasing. My function is increasing. And conversely, when my derivative is negative, that means my slope is negative. My function is decreasing. And finally, and really these are more specific instances of my derivative being 0. When I find my derivative is 0, I need to check to find is there a maximum or a minimum. And when my slope or derivative changes from positive to negative, then that point, that 0 that it changes from positive to negative, represents a maximum. So changing from increasing, my function's changing from increasing to decreasing, which means there is a relative maximum. Conversely, if my derivative, my slope, negative, if my derivative or slope was negative, going down, and then changes to positive, then my function is changing from decreasing to increasing, which means I can see here that I'm going from down, negative slope to positive slope, negative derivative to positive derivative, that I'm creating a relative minimum. These 5 topics here, these need to become as natural to you as taking a limit through substitution or as taking the derivative of a polynomial. These are key concepts that just need to be down. Based on this information, I can start drawing conclusions between a derivative and its graph, or between a function and its derivative. So assuming this is f of x, what approximately would f prime of x, what would my derivative look like? I find it's really easy to start with our minimums and maximums. This one right here at negative 1, 2, 3, 4. At negative 4, I have a derivative of 0 because this would have a horizontal tangent. And so at negative 4 over here, I'll plot a 0 value. Same thing at 1. I have a minimum, so that is a derivative of 0. And at 1, 2, 3, 4, 5, I have another horizontal tangent. So I have a derivative of 0 at 5. So I have 3 key points right here. Each of these points to the left, I have positive slopes, so I have positive derivatives. That's going to be a fairly high value at negative 7. So at -7, I'm going to choose something fairly up here, somewhere in here, as my value. I could estimate that slope by drawing the tangent line and say that's maybe about a +3 at -7. And then at -6, that looks more like a slope of about 1. And then I have my 0. Then I can look at these ones. We'll go in here. These are all obviously negative, so I should be graphing somewhere on the negative side of my chart here. That's the range I'm going to be. Because my function is decreasing, all of my derivatives between -4 and 1 are going to be negative derivatives. Looking at this one, it looks like approximately -1 at -2, approximately -1. And at -1, that's also approximately -1, maybe more of a -2. So we'll go a little bit lower. And then we see that our derivative, our slope levels out and becomes 0 again. On this side, at 3, I have a derivative of, that looks like maybe about 3. We'll estimate at +3, 3. And then it goes to 0 again. And now on the other end, at 7, this looks like a slope of about -2. So my derivative could look something like this. And then since my graph just continues off, my derivative is just going to continue off in the same pattern. Now your graph might look just slightly different than mine, and that's okay. But this gives us a basic idea of what our derivative would look like. And since our function is a polynomial, our derivative would also be a polynomial. So it would have nice, smooth edges as we travel. Let's look at this a little bit more depth in the graphical aspect and what kinds of questions we might be expected to answer on the AP exam. We're given the graph of f of x here, and we're asked to approximate the value of the derivative at f of 4. 1, 2, 3, 4. Now we're not given a point there, and it's not easy to tell. We could estimate. If we were asked to estimate, we might estimate graphically by drawing a line and trying to estimate, and we can do that still and kind of see where do we think this would fall roughly. And that's a little complicated, but it looks like that seems like my best point there and here, and that's a rise of 1, 2, 3, 4, 5 over 2. Graphically, I estimate 5 over 2. But I can also estimate this more exactly. If this is my point, and I'd say this is my tangent line, roughly, I can get a better estimate. I can get an approximation, and this is how we should do this when asked to approximate, by finding the slope between a point on either side. If I took these 2 points and drew a secant line through them, that secant line is roughly parallel to my tangent line. And if they're parallel, that means they have the same slope. If I find the slope of this secant line, that's going to be a very good estimate for the slope of this tangent line. So to do that, I'm going to find the slope between these 2 points. Slope is y2 minus y1 over x2 minus x1. My second point is 1, 2, 3, 4, 5. 1, 2, 3, 4. So the y will be 4, and my x will be 5. And my first point is over 3 and down 1. So my y is -1, and my x is 3. Which gives me 5 over 2, which I actually find that my graphical estimate was accurate in this case. We had a pretty good estimate. Our next question asks, at what values does the derivative equal 0? So let's think back. What is my information about derivative equals 0? And there's two things that we should think of here. My derivative being 0 should mean I would have a horizontal tangent line. And my derivative will be 0 anywhere that I have a minimum or a maximum. Looking at our graph, I can see I have a maximum here at negative 1, 2, 3, 4. I have a minimum here at 1 and another maximum at 5. And that my lines drawn tangent to those points would be horizontal. Therefore, I conclude that f prime of x equals 0 at x equals negative 4, x equals 1, and at x equals 5, because the function has relative maximums or minimums at these points. Number 3 asks a new question on what open interval. Open means that my interval is going to be encased in parentheses, meaning it won't include the ends. The very ends are those maximums and minimums, and they're not positive or negative. The derivative is not positive or negative. The derivative is equal to 0, so to find less than 0, I want to know where is my derivative less than 0. And when I think less than 0, if I think of, it just means negative. Where is my derivative negative? Where is my slope negative? Where is my negative slope means decreasing. Where is my function decreasing? And looking at the graph, I can see that I'm decreasing from negative 4 until 1. And then I decrease again starting at 5 and until infinity. I don't stop decreasing. So I can mark that f prime of x is less than 0 on negative 4 to 1 and 5 to infinity, because the function is decreasing. Conversely, where's the derivative positive? Well, the derivative being positive means the slope is positive. If the slope is positive, then my function is increasing. Where's my function increasing? Well, it starts from really low and starts increasing, so negative infinity, and it stops at negative 4. Then it begins increasing again from 1 and increases until 5. So I can indicate those intervals. F of x, f prime of x, is positive on negative infinity to negative 4 and 1 to 5, because the function is increasing. Next question asks, at what values of x, so I'm looking for x values, does the graph of the derivative go from being below the x-axis? So the graph of the derivative, our derivative, that's the slope of the function. And below the x-axis means negative. To above the x-axis, that would be positive. And what value comes between negative and positive? Well, 0 does. So I'm asking, when is my derivative 0, and specifically when does it change from negative to positive? And remembering, if my derivative, which is my slope, is negative and then becomes 0 and then becomes positive, this is going to happen at a relative minimum. Looking at my graph, I have a relative minimum at x equals 1 right here. So I can say at x equals 1, at x equals 1, because the function has a relative minimum. There we go. And then the last question asks, when does the derivative, we want to avoid it, when does the derivative or when does the slope go from being above the x-axis, that's positive, to below the x-axis, that's negative. So I'm saying, when does my slope go from being positive to being negative? That's going to happen at a relative maximum. Looking at my graph, that's at -4 and at 5. I would answer at x equals -4 and at x equals 5 because the function has a relative maxima. And we're finished with this page. One page left in this half of the lesson. Last graphical question. In the previous question, we were given the graph of f, given the graph of the function, and asked to answer questions about the derivative. In this question, we're given the graph of the derivative. We're given the graph of the derivative and asked to go backwards and deduce things about the original function. So our first question asks, on what intervals, open interval means in parentheses, is the function increasing? When is the function increasing? When I hear function increasing, that means it's going up. That means my slope is positive. That means my derivative is positive. And so I'm looking for, where is my derivative? And this is my derivative. Where is it positive, or where is it above the x-axis? And the only place on this graph that the derivative is above the x-axis is from -3 to 2. So we would say that f of x is increasing on the interval from -3 to 2. Because the derivative is positive. That's my justification. The derivative is positive. Second question, conversely, where is the graph of f of x decreasing? Well, my function's decreasing when it's going down, and it's going down, my slope is negative. My slope is negative, then my derivative is negative or less than 0. It also means that it's below the x-axis. Negative will be down here. Now I do need to watch something here. I start out being below the x-axis starting at -2, and I'm still below the x-axis, and I'm still below the x-axis, and I'm still below the x-axis, and I'm okay. At that moment, I'm no longer below the x-axis, I'm touching the x-axis. So I need to stop my interval right there and go from -2 to 2. And then I can add the next portion. I'm below the x-axis again on the other side from 2 until 4. So I have two separate intervals here. I'm excluding the points 2 because at 2 the derivative isn't negative, the derivative is 0. 0 is neither a positive nor a negative. So where is this decreasing? On -2 to 2 and 2 to 4, because the derivative is less than 0. Next question. At what values of x does the function have a horizontal tangent? Horizontal tangent is one of those keywords. We should think the derivative equals 0. Well, where does my derivative equal 0? Well, looking at my graph here, my derivative equals 0 here at -2 and here at 2. So I can say at x equals 2 and x equals -2 because the derivative equals 0. That's my justification. That's all it takes. Question number 4. At what values of x does the function, where does the function have a relative maximum? So looking at what a maximum would look like, a maximum is going to be increasing to the left and then decreasing to the right of it, meaning it's going to have a positive slope on the left and a negative slope on the right. It's going to change from a positive derivative to a negative derivative, and it's going to be 0 in between. I have to hit 0 in order to change from positive to negative. With this information, then I want to go back and examine my graph and find where does my derivative change from positive to negative. And the only place my derivative changes from positive to negative is right here, because this is my only place I have positive. So it changes from positive on this side, to negative on this side, meaning that I have a relative max at x equals 2. So I'd answer at x equals 2 because the derivative changes from positive to negative. Then on the other side, where does the graph have a relative minimum? So a minimum looks like this. I start with a negative derivative, and then I hit 0 and become a positive derivative. My function goes from negative derivative to positive derivative. So I want to look at my graph and see where does my function, where does my derivative change from negative to positive? Where does my derivative change from negative to positive? And I have negative here, 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 here. Here it goes from negative to 0, but it doesn't go from negative to positive. It goes negative, negative. So nowhere. At no point do I change from a negative derivative to a positive derivative. The answer is there is no relative minimum. There's no relative minimum because the derivative never changes from negative to positive. Sometimes the answer is there isn't one. I still need to justify, how do I know that there isn't one? Well, I know there isn't one because a relative minimum has a derivative that changes from negative to positive, and no place did my derivative function, the graph of my derivative, show that it changed from negative to positive. Last two questions for the first half of the lesson. What is the slope of the tangent line to the graph at f of x equals 0? So to find the slope of the tangent line of the function, slope of the tangent line is the derivative. And we want to find the derivative at x equals 0. So what is the derivative at 0? Well, I'll go to my derivative and read the y value at 0, which is -2. That's where my function exists at x equals 0. So my derivative at 0 equals -2. My justification is because the slope of the line drawn tangent to f of x at x equals 0 is the value of the derivative at 0, which equals -2. And that's it. We're just putting that into words and writing it down. That's the verbal element of our calculus. The slope of that tangent line for a given function is equal to the derivative at that value. And we read the derivative off of the graph, and the value we read was -2. What is the slope of the normal line? Remember the normal line is the opposite reciprocal of the tangent slope at x equals 4. So to find this, I want the opposite reciprocal of the derivative at 4. This will be the slope of my normal line. So I want to find what is my derivative at 4. Go up to the graph. At 4, my derivative is -2. And plug that in. -1 over -2 is +1/2. So the slope of my normal line equals +1/2. Slope of the normal line is 1/2 because the slope of the tangent line, the slope of the tangent at x equals 4 is the derivative at 4. So the normal line is -1 over f of 4. And I've provided my explanation. So hopefully this helps us to understand the connections between increasing and decreasing of a function. Is the derivative being positive or negative? Because the derivative is the slope. The slope of the tangent line at that point, the slope is the derivative. Where the derivative is 0, I have a horizontal tangent and potentially a relative minimum or a relative maximum. And I can verify exactly which of those I have, a maximum or a minimum, based on whether my derivative changes from positive to negative for a maximum or from negative to positive for a minimum. And we've applied that to finding tangent lines and normal lines, and we could actually find the equation of this tangent line using the point at x equals 0 and so forth. In the second half of the lesson, we'll look at how can we find these increasing intervals, these decreasing intervals, these minimums and these maximums without a graph, when I'm just given a function analytically and I need to find where is it increasing. This is where being able to take the derivative analytically and then test, is my derivative positive here or is my derivative negative here? We'll be able to put that into application in the second half of the lesson.